Exponential equations. In this unit, we will be studying exponential equations and their graphs. Exponential equations are in the form y equals a times b to the power of x. Now, this equation may look familiar to you. We have studied something that is very similar. Recall our last unit on geometric sequences. You'll notice that exponential equations and geometric sequences have very similar equations. Okay. Instead of t of n in geometric sequences, we have y equals, okay? And then notice that they both have an a that comes next, and in sequences, a was the zero term. In exponential equations, a is going to be the y-intercept, okay? So very similar. You'll notice that there's the common ratio in this geometric sequence equation. In exponential equations, we have what's called the multiplier, okay? It's the same concept. And then you'll notice that for geometric sequences, we have n, which stood for the term number, and we have an x in exponential equations, which stands for the input, okay? And then t of n, which was the actual value of the term of the sequence, is replaced by y, which stands for the output, okay? And an important difference between these two is that in exponential equations, when you graph them, they have a continuous graph, which means you connect the points that we find, okay? Geometric sequences, if you remember, they had a discrete graph, which means we only graphed the actual values of the sequence, and there were no values in between terms of the sequence. Okay, so here is an example of a geometric sequence and an exponential equation. On the left is the geometric sequence, and you can see the zero term was 3, which is actually not a term of the sequence. So you'll notice on the graph, there is no 3 graphed. And the multiplier was 2. Okay, so if you look at the sequence terms, they're doubling as we go. So 6 became 12, became 24, became 48. Okay. Now, that same situation as an exponential equation on the right, you'll notice the zero term is 3, which is the y-intercept. That is a point on the graph, okay? 0, 3. And then you can see the multiplier is 2, so points are doubling. So 6 to 12 to 24 to 48. But notice on the graph that we graph a continuous graph. So there's a line between the points, okay, which shows that this is a continuous graph, where when we study geometric sequences on the left, we do not connect the dots in that case, okay? So this was called a discrete graph, and this is called a continuous graph. All right? But otherwise, very similar in the way we think about them, okay? So one thing we're going to have to be able to do is fill in a table using an exponential equation. Okay, so here's our equation, and there's the table, so we'll try to fill that in. So for term 0, or the y-intercept, we would just plug a 0 in for x. So this would be 5 times 2 to the 0 power. Now, 2 to the 0 power is just 1. In fact, anything to the 0 power is just 1. So this would end up being 5 times 1, which is 5. So in the table, that value would be a 5. Now, also, you can just think of the equation and realize that the number outside parentheses is the y-intercept. Okay, so if you have the equation, it's pretty easy to jump to the y-intercept value. Now, for when x is 1, we're going to plug a 1 in for the exponent. So it would be 5 times 2 to the first. And then remember our order of operations, we have to do exponents first. So we would do 2 to the first, which would be 2. So this would be 5 times 2 is 10. And then for the second term, we'd plug in a 2. So now I'm looking for the second term. So I would do 5 times 2 to the second. And again, we do exponents first. So 2 to the second is 4. So it'd be 5 times 4 is 20. Now, one thing you may notice as we're moving on here, 2 is the multiplier, which means that, from one term to the next, if our x's are going up by 1, that our y's will be doubling. So you can probably guess that for 3, the answer would be 40, and for 4, the answer would be 80. Okay, but you can still plug them in if you wish. To find the third term, you would do 5 times 2 to the third. And then 2 to the third would happen first, so 2 times 2 times 2 is 8. So it'd be 5 times 8 is 40. And then for the fourth term, of course, it would be 5 times 2 to the fourth. Again, we do 2 to the fourth first. So that would be 2 times 2 times 2 times 2, which is 16. So it'd be 5 times 16 is 80. Okay, so that's how we fill in the table. Just plugging in inputs for x from our x column and solving it for y. Being careful about the order of operations because you have to do the exponents first. Now, if you want to do these on your calculator, it is possible to do it all in one input, but you have to type in everything. So you'd have to type in 5, 2 to the third, for instance, all in one command, and that would just give you automatically 40. Okay. Remember, the one thing you can't do on these type of problems is simply multiply the 5 times 2 first and get 10, and then take 10 to the third power. That will not work. Okay, you will not get the correct answer. So be sure to follow order of operations. So here's the table we just made, and I wanted to show you the graph. Notice 0, 5, that's the y-intercept, so make a dot at 0, 5. 110 is right here. 240 or 220 is right here. And none of the rest of the points fit on the graph, okay? But we can connect them anyway. So starting off at the upper right, at the 220, and we could put arrows on the end of these because these lines in each direction go on forever. And notice that as we go to the left, this keeps getting smaller and smaller and smaller until it gets really close to the x-axis. This is the x-axis. Okay, so that is an exponential increasing equation. Okay, and we call that exponential growth. Now, here's another example. This is called exponential decreasing equation or exponential decay. Okay, so this is decreasing or decay. Now, one way we know that is that the multiplier, the b value, is a decimal. Okay, if this is a decimal or a fraction, we know that this equation will be decreasing, kind of like our decreasing geometric sequence. Okay, so I need to fill in the table for this, and one thing you'll notice again, the y-intercept is always the number that's outside the parentheses, so our y-intercept here would be 20. Okay, you could also just plug in a 0 for the x, so it'd be 20 times 0.5 to the 0, and anything to the 0 power is always 1, so this is really 20 times 1, which is just 20. So that's our y-intercept. Then for the first term, we would plug in a 1 for x, so we'd get 20 times 0.5 to the first, and 0.5 to the first is just 0.5, and 20 times a half is 10. Okay, so if you remember from our geometric sequences, when the multiplier is 0.5, it means that we are cutting our number in half, our value in half, every time we go up 1 unit. So you can probably imagine how to continue this pattern. It'd be 20 down to 10, and then 10 cut in half would be 5, 5 cut in half would be 2.5, 2.5 cut in half would be 1.25. And of course, if you wanted to, you could take 2 and actually plug it in for x. So it'd be 20 times 0.5 to the second. And 0.5 squared is 0.25. And 25% of 20 is 5. Okay, so it is okay to keep plugging in your input values, your x values, into the equation, and then solving it for y. Okay, but you'll notice these numbers are getting progressively smaller, just like in a geometric decreasing sequence. If we want to look at the graph, here's a graph of that table. Again, we're going to show the y-intercept, and we'll show any points that we can fit on the graph. On this one, we can fit them all in. Okay, and for the decimals, you just do the best you can. And of course, there would be arrows on the end of this. My program doesn't put those on there. So it goes on forever in both directions. And you'll notice again that the bottom line here, as it goes to the right, it's hugging that x-axis. So it's getting very, very close to that. Okay. Now, one quality that we'd like you to understand about these graphs is that they have what's called an asymptote. Okay, and an asymptote is a line that a curve approaches but never touches as it heads towards infinity or negative infinity. What I mean by that is, you'll notice this graph seems like it touches the x-axis in this case, but it actually doesn't. Okay, it just keeps getting closer and closer and closer to the x-axis, but never crosses it. Okay, that means that the x-axis is an asymptote for that graph. On the right, our exponential growth equation, you'll notice that going to the left here, when x's are getting smaller, that line is also hugging the x-axis, but it never crosses it. Okay, it just keeps getting closer and closer and closer and closer to it. That makes the x-axis an asymptote on that one as well. So the x-axis is an asymptote for the graphs above. The exponential curves get closer and closer to the x-axis as they go to infinity or negative infinity, but they never, ever touch it. Okay, and that is a property of exponential equations. Okay, they will have an asymptote like that. There is no asymptote in the other direction. So this way, it's not hugging any line. It's just going on forever and ever and ever, increasing and getting larger and larger and larger y values. Okay. All right. Good luck with exponential equations.